increasing and decreasing entropy when you trace the environment or conditionalize to the subject. This is very clear. In fact, it's very close to the relational view that I will talk later. But I didn't understand a word about the how inflation plays into that. You were very fast there, so I suppose I could look at the paper. But maybe you could just say a word. What I understood has to do with degrees of freedom, Hilbert space, tracing on that, which doesn't seem to have nothing to do whether things become large or small and blows or don't blow. It seemed to be irrelevant, that. So where does it come in, the actual...
Okay, so the basic reason I gave, went through it very fast, but because I didn't want to upset the very patient chair any further. And the basic reason it works, the basic reason that long-distance correlations help is because what that means is that, for example, if you're trying to find out whether you are in an inflationary region or not, if this little piece here has inflated, so with very large likelihood have all the ones near it, right? So each little bit of information you learn about now is no longer telling you something just about what's there. It is also telling you a lot about what's much, much farther away. Or to take a solid state example, suppose you have water that's super cooled and half of it is frozen to ice in large swaths. If you look at just one little place and you say, oh, that's frozen, that tells you a lot about the surrounding area also. So you learn a lot, you learn about a big region with a lot of bits from just looking at one bit. That's sort of the most intuitive explanation I can give.
Does it violate Shannon result that the amount of entropy decreases exactly by how much you get relative entropy with it?
It does not violate. It's interesting that you don't get Shannon's result that you decrease always by the mutual information. And it's easy to see that the result in quantum mechanics has to be more complicated, because if you just have two qubits perfectly entangled, right? Then the mutual information in classical physics is 1 bit, but in quantum mechanics you know it's 2 bits. Right? So if your knowledge about that one other bit that you're looking at were to decrease by 2 bits, then suddenly you would have an entropy of -1 bit, which it cannot. So quantum mechanics, you can never reduce quite as much as that. But the spirit of Shannon is still very much true. You find that you never get any sort of crazy behavior like this. And on average, your entropy does decrease exponentially like this, which I was very surprised when I got the result, but the more I think about it, the more I've come to appreciate inflation.
There's a quick question about this sort of cosmological entropy problem that people sort of latched on too long ago, that the biggest black hole you could fit in the universe would have an entropy of 10 to the 120 and the number of photons 10 to the 89, and so Penrose had always argued, we're nowhere near the maximum entropy.
Right.
It all seemed to me that after 1999 that argument doesn't seem correct, because when you discover the cosmological constant, let's suppose that's the reason for the acceleration, then you've got a 10 to the 120 entropy tied up with that. And so we're actually very close to that maximum entropy. And there is no entropy gap that Penrose has been arguing. The argument should have changed in 1999. Do you agree with that?
Well, I certainly agree with you that the basic argument Penrose makes is ultimately not correct. I still feel that there is something left for us to explain, because even if we forget about our universe, the entropy in this room could obviously be much higher than it is. We could all be dead right now in heat death, and we're not. So maybe it's not 30 orders of magnitude, maybe it's only 10 orders of magnitude, but that's still a lot more. It still deserves an explanation, and I think inflation provides it very nicely, because if you start out with this picture here, and bear in mind that what we're actually not creating is just one of these branches, but we're creating all of them, then it doesn't matter if... So both Sean Carroll and Roger Penrose basically say that the problem is that the entropy of the whole thing now will equal the entropy of the whole thing in the beginning. That's what the argument hinges on, right? And that inflation